Welcome. Today we are exploring two essential skills, combining simple programming blocks into complex algorithms and testing them to ensure they function as intended. Real-world programs rarely rely on a single, isolated command. To solve meaningful problems, you must connect different logic structures together. This diagram illustrates a technique called nesting. As you can see on the right, we have placed a green if-else selection block entirely inside a yellow for loop. Nesting occurs when you place one programming construct directly inside another. Think of it like wooden nesting dolls, or putting a smaller box inside a larger one. The inner block is completely contained, meaning its execution is entirely controlled by the outer loop. By stacking these basic rules, you turn simple, repetitive tasks into dynamic algorithms capable of complex decision-making. The most common combination involves placing a selection, an if statement, inside a count-controlled loop. When you do this, the outer loop continues its cycle, but the inner if statement makes a new decision on every single pass. Let's trace a practical example. Imagine a system grading 5 student test scores. If a score is over 50, the output is pass. Otherwise, the output is try again. Because of this nested structure, the computer evaluates the passing criteria from scratch for every individual student in the sequence. We can track this using a trace table. Student 1 scores an 80. This triggers the greater than 50 condition, and the system outputs pass. The loop cycles to the next pass. Student 2 scores a 40. The condition fails, outputting try again. Now, what happens on pass 3 if student 3 scores exactly 50? 50 is not greater than 50. The condition is false, so the student receives a try again. In written code, whether in pseudocode or Python, we use indentation. By pushing the if-else block to the right under the loop, we create a visual map showing which instructions belong inside it. This indentation is the structural map that dictates how the computer's execution flows from top to bottom. Writing code is the first step in a continuous loop. Building reliable software requires a cycle of designing, developing, testing, and improving. Once written, test your algorithm against 3 data types. Normal data, like 75, proves it works for expected inputs. Extreme data, like 0 or 100, verifies boundary handling. Invalid data, like words instead of numbers, must be caught safely to avoid crashes. Combine constructs to build capability. Track execution with a trace table. Use 3 data types for testing. An algorithm is only as reliable as the tests it survives. By actively trying to break your logic, you ensure it functions correctly in the real world.